Hello everyone, welcome to the first lecture of week 9 of the course Power Network Analysis, in which we continue our discussion on power flow analysis, third last module of this course. Today's discussion we will discuss a furthermore extended version of fast decoupled power flow, which we call as the DC power flow or the DC model. The previous discussion, we had talked about fast decoupled method extensively. I would request the viewers to please go through the previous lecture on fast decoupled power flow, fast decoupled method before going into the current discussion on DC power flow. That will help better understanding the discussion we're going to have today. So DC power flow, or essentially the DC model of the system, it is at the outset I would say it's a approximate model. It's not a practical or accurate model. It's an approximate model which power system engineers or power network engineers over the years with their experience of how network operates have figured out this model that, okay, if this model were to be used, which is not a realistic model, it's just an approximate inaccurate model. Even if this approximate model is to be used, the corresponding solution that we would get out of this DC model, which is a fictitious model, it would still be acceptable or close enough to the actual solutions that we would get from Newton-Raphson power flow for actual network or fast decoupled power flow for actual AC networks. Essentially, the overall bottom line story is that this DC model of the network, it's a fictitious network which power network engineers, through their experience of how network operates, have come up with this model, and the solution, the power flow solution essentially obtained from this particular model is almost acceptable to the solution that is obtained from actual AC nonlinear techniques of solving power flow equations under certain operating conditions. So what are those operating conditions? So in a way you can understand that, okay, if there is a simpler model which can be solved compared to an actual nonlinear model, then obviously people would solve this simpler model wherein the accuracy is not that bad, and simpler model solving would definitely require lesser time, lesser effort, and the effect of it would still be the more or less similar to the actual nonlinear model. So that's where the DC model comes in. It's an approximate inaccurate model. And as I have probably mentioned, it's a linear model of the actual AC network, whereas the previous techniques that we have seen, whether they are Newton-Raphson, Gauss-Seidel, or fast decoupled, they all involve nonlinear model of the AC network. So this model of the network, it is acceptable to power network engineers when the operating conditions are such that the network is not loaded in terms of real power or reactive power flows, essentially, which means that the line flows are not very high. The line flows, they will not be very high when the system load is not very high. So voltage profile under that condition would be more or less flat because flows are less, load is less, source is already there. The corresponding lines do not have to carry significant amount of current. The potential difference need not be higher across those lines when the flows are to be lesser because load are lesser. And the important part is the corresponding R by X ratio is very small. This is only for transmission lines. So under such conditions where the system is operating under these two aspects, where flow is not very high, means the load is very small. It is not very high. The network has higher current carrying capacity. It is not satisfying those conditions. The load is very small. So basically it is like light load condition. Under those conditions, this DC model of the network would give us acceptable, appreciable values. And the assumptions involved in this DC model are all elements of the network which regulate voltages or reactive power flows, they are to be neglected. Because we are assuming that the voltage profile is not very different, the voltage profile is sufficiently flat, that means almost all voltage magnitudes of buses are equal to 1 per unit. So there is no need of considering any element like line charging susceptance, shunt factors, regulators, line resistances, which are going to impact these voltages because voltages are not changing much under light load conditions. Only those elements which can affect the real power flows, essentially the phase angles, those are to be considered, and that's the reason why phase shifters are only considered, line reactances are only considered. And if you correlate this, then these assumptions were also applicable while evaluating B dash matrix in fast decoupled power flow. The same assumptions are being applicable here, and that's the reason why I mentioned DC model or DC power flow is an extension of fast decoupled method. The voltage phase angle variations are small, the differences are small, so sine terms, they are similar to the phase angle difference themselves, whereas the cosine terms are almost all close to 1. Network has infinite reactive power generation and absorption capacity, and that's the reason why voltage profile at every bus in the network is sufficiently flat. So in a way, in DC model of the network, elements which pertain to reactive power, injection flows or voltage magnitudes, all of them are ignored. Only those elements are considered which impact the voltage phase angles and the corresponding real power flows, and that's the reason where we would come up with our DC model. So in a way, you can expect that in DC model or DC power flow, there are no equations involved from power flow perspective which solve for reactive power or voltage equations. Only equations pertaining to real power flows and corresponding voltage phase angles, they would be considered. So as a result, the voltage at all nodes is equal to 1 per unit because the profile is almost flat, infinite reactive power capacity exists. And if we look at our real power injection equation at bus I, then since voltage magnitudes are close to 1, so these terms become close to 1. Cosine of theta k, theta I is equal to 1. Gik is not to be considered. Why? Because all line resistances are neglected, certain susceptances are neglected, voltage regulators are neglected. If resistances are neglected, where would we get the real component in Y bus with respect to conductance? G would also be 0, so this is equal to 0. So essentially we are left only with minus Bik, and this sine term is equivalent to or approximate to theta k minus theta I, which is where this term comes in. If we rearrange our terms, it would get expanded into this form. We redefine or change notation of Bik and Bik sum over here. We denote them as Bik 0, which is minus B of Bik, which is basically a non-diagonal or a off-diagonal term, and Bi0 is essentially a diagonal term of a matrix. That matrix we would call that matrix to be, let's say, B0 matrix. So Bii0 is the diagonal term of B0, and Biik0 is of diagonal term of B0, where k is not equal to I. So under this B0 definition, we can express the real power injection at every bus in terms of the voltage phase angles and the corresponding B0 elements. If we put it in a vector form, then this is the equation that we get, where B0 is a n cross n matrix, theta is n cross 1 vector, and P0 is n cross 1 vector, depending on what type of source or load is connected at the corresponding bus. The corresponding terms would be 0 or non-zero from the generation perspective. We expect that every bus would have at least a demand on it or at least a non-zero injection on it. This equation is what is called as the DC power flow equation. B0 matrix in this DC power flow equation is a rank deficit matrix. In fact, its rank is always n minus 1 for a n bus network, provided that n bus is sufficiently connected to the ground for voltage phase angle measurement perspective. And that's the reason why the rank deficiency comes in, because since our power flow equation, they are functions of difference of voltage phase angles. So it is essentially impossible to determine all voltage phase angles uniquely at a given point of time, and that's the reason why one voltage phase angle has to be chosen as a reference. We call that reference bus, similar to bus 1, as slack bus or angle reference bus or swing bus. And hence the angle reference bus reference value is chosen, which is usually 0 degrees or radian, although the importance of choosing it to be 0 need not be, it is not essential. It can be any non-zero value also. Correspondingly, the phase angles of other buses would adjust themselves. So since for slack bus or angle reference bus, the reference value is known. So theta 0 is essentially the unknown vector is essentially theta I for all I ranging from 2 to n if bus 1 is the angle reference bus. And that's the reason how the rank deficiency part of B0 can be handled, because if B0 is a rank deficient matrix, then theta 0, which is going to be B0 inverse P0, this inverse cannot be evaluated because it is a rank deficient. To make it indeficient, one of the angle references has to be known, and that's how the B0 matrix becomes n minus 1. So corresponding theta 0 becomes n minus 1 cross P. P0 also becomes n minus 1 cross 1 vector, because for slack bus or angle reference bus, the corresponding injection is infinite, similar to the choice that we had for angle reference slack or swing bus in the initial discussion. Since the orders are changing for phase angles and the known injections, we denote the new matrix to be B dash matrix, which is actually component or element of B0 with reference bus row and column removed from B0 matrix. And this B dash matrix, it would trigger or indicate that this B dash matrix is the same B dash matrix that we have seen in the P theta half iteration of fast decoupled method. And essentially that's how decoupled power flow and DC power flow, they are interrelated. Essentially, indirectly in DC power flow, we are only solving E1 equation for fast decoupled method. The E2 equation in fast decoupled flow is not being solved in DC power flow. So once the B dash matrix, which is now n minus 1 rank matrix, because one row and column for slack bus has been removed from there. So B dash inverse can exist, and we call that inverse to be X matrix. So all phase angles for buses except slack bus can be known with respect to known injections in every bus. It is a linear method. There is no iteration or important dependency. There is no dependency of X on phase angles or voltages. So X again is a constant matrix. B dash again is a constant matrix. DC power flow is solved. When it is solved, it gives a solution only in one go, because it's a linear method. There is no iteration involved, and there is no need of any initial choice also. The solution that we get from DC power flow are only the voltage phase angles. Voltage magnitudes are chosen to be 1 per unit. So it's basically a purely reactive model. There is no real power loss involved in DC power flow because line resistances are all neglected. So once we obtain those phase angles, we can put in those assumptions which we had for real power injections for real power flows also, where V square would be equal to 1, these terms would be equal to 1, GIK is 0 because line resistance is not considered. So basically this term entirely is 0. We are only left with let me check. So this term entirely becomes 0. We are only left with this one term. This is approximated as theta k minus theta I, and which is what we get here. So once we get our voltage phase angles, we can put in those numbers here and get the corresponding real power flows also. DC power flow as extended version of fast decoupled method, it also serves as a very critical tool for fast contingency or security analysis. It basically gives reliable bus voltage phase angles for nominally loaded or lightly loaded transmission networks. Transmission networks whose voltage profile is almost equal to 1. All buses are having similar voltages. Line flows are much smaller. We will understand the importance of DC power flow through this example here. I have chosen a similar network. The only difference is in previous networks we had bus 2 as our PQ bus, bus 3 was our PV bus. Since we are talking about DC power flow where voltage magnitudes and reactive power flows are not to be considered, so I have chosen bus 3 to be now also a load bus. There is no source present here, it's only a load bus. That's the only difference. The line reactances, they remain the same. Since reactive power injections are not important for DC power flow, so we are only dealing with real power flow injections. We are considering two conditions. Bus 1 is angle reference bus on which there is a source connected, and bus 2 and bus 3 are having loads of PD2 and PD3. Under light load condition, PD2 is 0.4 per unit and PD3 is 0.2 per unit, whereas for heavily loaded condition, PD2 and PD3 are becoming 5 times of their respective values under light load condition. So under these conditions, if we were to solve our actual Newton-Raphson power flow, be it in polar version or rectangular version, the process would remain the same. Newton-Raphson power flow, there would be no PV buses involved. We would treat PQ buses, bus 2 and bus 3 to be PQ buses. Qs essentially are all 0. So QD3 is also 0. QD2 is also 0 for Newton-Raphson power flow. Bus 1 will remain as slack bus. If we solve this network for AC power flow with these information and find the corresponding line flows under two conditions, one is the light load condition and heavy load condition, then these would be the actual flows. I have not intently given the voltage information because that is not important, although that could also be shown. The important part is, having solved the AC power flow solution equations for this given network under this condition, we can use that voltage to find these line flows the way they have been discussed earlier. So let us see that can our DC power flow also provide these flows, because as I mentioned earlier, discussed earlier, DC power flow can give acceptable values of flows under certain conditions. So let's see that. So how do we proceed with DC power flow? We find the bus admittance matrix, the way it is usually evaluated. We take B0 matrix from here, which is negative of B. Since bus 1 is slack bus, so we remove row 1 and column 1 from B0 and we get B dash as our 2 cross 2 submatrix present over here. The unknowns are voltage phase angles of bus 2 and bus 3. For known injections at bus 2 and bus 3, bus 2 and bus 3 are load buses, so the corresponding injections are minus 0.4 and minus 0.2 for light loaded condition. Since B dash is known, it's not a singular matrix, so we can get the corresponding phase angles. These are in radians, please note, these are in radians, not in degrees. And from these angles, we can actually evaluate these corresponding flows through the expression which was discussed earlier. Now, if we compare these flows are more or less equal to till the third or fourth decimal to the flows that we have obtained from actual AC power flow also. So if you compare the numbers given over here on slide 9, which was the actual AC power flow solution, with the DC power flows that we have obtained for light load condition, the solution or the flows match till the fourth or the fifth decimal. That indicates that under lightly loaded condition, DC power flow can also give similar acceptable real power flows as compared to AC power flow, and hence the need of solving AC power flow can be avoided if required. For heavily loaded condition, if we follow the same process of solving DC power flow, the flows that we would get, they would be matching till, I think, till the second or the third decimal only compared to the solution which is shown over here. The accuracy or the error has gone up, and hence the corresponding accuracy has gone down. So accuracy of DC power flow has decreased compared to AC power flow with increase in line loading as discussed earlier. In fact, these flows that I am stating here, P12 AC or P13 or P23 AC, what are these P12, P23 and P23? P12 is the flow from bus 1 to bus 2 on line connecting bus 1 and 2. P13 is the flow from bus 1 to bus 3 connecting line bus 1 and 3. Similarly, P23 is the flow from bus 2 to bus 3 connecting line bus 2 and 3. And the other counter flows, they can also be defined. So here we can have P31, here we can have P32, and here we can have P21. Since the line resistances are absent, they are not considered. If you add up P12 and P21, which should actually be the loss on line 12, since it is a lossless network, this addition would always be 0, and that is where this negative components or terms mean. There is no resistance, so there is no I square R loss. And same is also being observed in the DC network condition also, although the accuracy of DC power flow solution has gone down because of heavy loading compared to light loaded condition. That's all for today's discussion. The next lecture, we will continue with the power flow analysis technique or module, and we would discuss the technique which is very specific for distribution networks, of how power flow can be solved for typical radial distribution networks where R by X ratio are high compared to R by X ratio in transmission networks. Why the ratio is high in distribution networks, that we will also discuss in the next lecture, and see that a technique specific for distribution network, what is that? We call that as backward forward technique. And distribution network power flow, it is generally not easy to solve by Gauss-Seidel or Newton-Raphson. Forget about fast decay or DC power flow, they are not at all even applicable, because distribution network has its own physics, has its own phenomena, and hence we need dedicated technique for that. That's all. Thank you.